Right, so we are getting down to the final few topics of multivariable calculus, the final topics of vector calculus, really. So we've talked about surface integrals over actual surfaces, actual functions. We've talked about surface integrals of function fields over different surfaces, and now it's time to talk about surface integrals for vector fields. So now, if I have some surface, if I have some arbitrary surface like that, and I define tons of different vectors in a vector field, right, I want to consider, if I integrate all along the surface, what is this vector function or this vector field doing to the surface, right? So you can imagine heat flow and all that sort of stuff. We'll get into that in the application section of today's show. Now, the definition that I want to go over today is the one for surface integrals over vector fields. Big surprise. So we want to let f be some continuous function or vector field over some surface S with a unit normal vector n. So what's a unit normal vector? The unit normal vector is simply a vector on a surface that is normal to the slope. Now, what does normal mean? Well, what normal means is normal means that it points perpendicular in every direction to it. So imagine like taking a little cross product on the surface of two parallel vectors with respect to each kind of variable of the surface of the parameterization. It provides a little vector, a normal vector. And that normal vector can represent an area. So we really get into the idea of representing an area with a vector. Now, a vector can have a direction. So why is this important? So consider a little area, right? Like this. And then consider a vector field going like this. The vector field is going like that onto the area. Now, the area of this can be represented by a magnitude, and the direction of this area, the orientation of the area, can be represented by a vector or by a direction. So we could have a unit normal vector, which is normal to the surface of this little area, and consider we want to take like how much of this fluid is going through. If the vector field is the fluid and then the area is this little vector, to consider like how much fluid is going through, we would dot it with this vector with the normal vector. So that's the vector f, a little vector df, and this is a little vector dA. And we dot df with dA to kind of see what the deal is, to see kind of how much of df is going through dA, right? So you could imagine like if the unit normal vector is perpendicular to the force vector, then there's going to be no kind of flux on that area. But if it is parallel, if both of the vectors are parallel, then it's going to be like full. That's going to be like the maximum that you could possibly have. Anyways, if I want to take the surface integral of a vector field f over ds over s, then that can be rewritten as the double integral over the surface of f dot the unit normal vector with respect to the differential surface element. And then we can further rectify this by looking at the definitions that we had earlier in the last couple of videos, where we take the double integral over the domain D of f dotted with the r sub u crossed with r sub v dA. Now, the r sub u and r sub v are obviously the partial derivatives to whatever two-variable parameterization you use to describe said surface. Okay, hope that all made sense. Let's try an example. Maybe that'll make more sense, you know. Now, we would like to find the flux of the vector field f equals z e sub x plus y e sub y plus x e sub z. Okay, and we want to find this across the unit sphere. Fortunately, we have many parameterizations from the unit sphere that we've already kind of looked at, so we are going to use the parameterization with the spherical coordinates. However, we don't need the rho because we already have a constant radius across the sphere, so we use the theta and phi. Okay, anyways, putting this into the theta phi parameterization, we get f is equal to cosine of phi e sub x plus sine phi sine theta e sub y plus sine phi cos theta e sub z. Now, this should all also make sense because this is the spherical coordinates parameterization we've been using forever. Now, if I want to cross the partial derivatives, I'm not going to go through this because we've done this countless times. We get sine squared phi cosine theta e sub x plus sine squared phi sine theta e sub y plus sine phi cos phi e sub z. Okay, so now I want to dot this with the vector field itself in the theta phi parameterization with r sub phi cross r sub theta. And I get cosine phi sine squared phi cosine theta plus sine cubed phi sine squared theta plus sine squared phi cosine theta. Okay, so I hope this all made sense as well. Now, at last, we are in a position where we can plug this in the integral, such the integral of f ds is equal to the integral from 0 to 2 pi, remembering the bounds, is then 0 to pi. We integrate with theta and phi, and that's of 2 sine squared theta, or 2 sine squared phi, cosine theta, plus sine cubed phi sine squared theta. Now, this is a whole integration you can do. It's a fun one, I guess, integrating first with respect to theta, then with respect to phi. You can do that. Anyways, you have all of the tools you need from Calculus 2, and you can go check out the videos in Unit 6. I recommend you do so from single variable calculus. And anyways, from this we get the answer of being 4 pi over 3. Okay, so I hope this all made sense. Now, what we'd like to do is we'd like to expand this idea, right? We have a really powerful tool for finding the flux through an surface, the flux through a surface. And, well, where have you heard the word flux? You may have heard the word flux from electromagnetism. Well, yes, we are going to get into electromagnetism now. Here are some of the applications of the surface integrals over vector fields. Let E be the electric field. Then we have the rule for Gauss's law, okay? So what Gauss's law says is it says essentially if I have a surface and I have let's say I have a surface, right? And I have some Q, enclosed. I have some Q, charge Q in there, right? The surface has a charge Q. And that is equal to some constant times the double integral over a closed surface. That's why I have the little circle around the two integrals, because it's a closed surface, just like we had the one around the circle for the contour. But anyways, what we can do is we can take the E field and dot it with the area. So it's essentially saying if I take a little electric field and I dot it with the area displacement, it says what is going to be the flux through there. So E epsilon naught over phi, this can be written more succinctly as epsilon naught Q over epsilon naught equals the integral of E dA, but we can write Q0 over Q enclosed over epsilon naught as phi, and phi is equal to the flux, the electric flux. So it basically says the flux is equal to the flux integral. And this is a little bit more, this makes a little bit more sense when written in differential form. Gauss's law has a differential form that says that the divergence, if we remember the divergence of the E field, is equal to rho over epsilon naught. So it basically says that the amount of stuff coming out or going into a little place is equal to the charge density over epsilon naught, which is equal to the charge. Okay, that should make sense. Now, we also have the idea with heat flow. So we can let temperature be some function of x, y, and z. We'll call it u. Thus, the heat flow, the force, is equal to negative k, which is a constant, times the gradient of u. Then we can say that the force integral, the flux integral, is equal to negative k times the double integral over the surface of w dot ds. Okay, so this is how kind of we can use these rules and these surface integrals in order to make our lives easier in multiple different fields. Now, it turns out Gauss's law is actually meant as a method to make it less likely that we would need to do integrals by choosing surfaces correctly. So say we choose for a point charge, we choose a sphere, and that way we don't really even need to integrate over it because we know what the volume of a sphere is. And that, of course, gives us the famous constant K for the Coulomb constant. So it would save you needing to integrate over lines and all of that for your electric fields. Anyways, that's getting a bit ahead of myself. Or actually behind myself, because that's from Calculus 2. So that is surface integrals. Thank you very much for watching, and we'll see you next time to talk about Stokes' theorem, or the fundamental theorem of the curls. Thank you.